Hello and welcome to our final lesson in Chapter 15 on rationals. Today's lesson deals with a change in the end behavior, something called oblique asymptotes. Our objectives are to determine the following for rational functions with a higher degree expression in the numerator. We want to write an equation for the end behavior, and then if exactly 1 degree higher, we want to sketch the graph. So for instance, when you look at this equation, you have a degree 2 over degree 1. That one we should be able to sketch the entire graph. A graph like this where it's 2 degrees higher on top, we'll sketch the graph, but the main focus there is to write the equation for end behavior. But first let's revisit an old friend, the equation where we have the same on top and bottom. That gives us a nice horizontal asymptote. If I gave you this equation and had you find the zeros, fairly straightforward. -2, we have a vertical asymptote when the bottom 0. Plug in 0, you get the y-intercept. We would know that the horizontal asymptote is the end behavior. I want to get back to some language that comes up more so in calc maybe. We talk about a limit as x approaches negative and positive infinity, and I put the negative on top to say the left, and then the bottom is positive infinity. Then the function f of x will approach, as we see in the equation for the horizontal asymptote, the function approaches 2. All right, so if we did our sign chart and did all the work here, we would see a graph that looks like this, nice straight horizontal line. In today's work, we're going to get an oblique asymptote, sometimes called a slant asymptote. Now, how is the end behavior affected when the numerator degree is greater than the denominator degree? The numerator being more affected by extreme x values, you're squaring it as opposed to just linear, or it's always at least 1 degree higher on the top. It gets affected more by those large values. And so what we do is we take the function in this form, nice rational form, and we'll do long division or synthetic division, come out with stuff that goes in nicely, and then a remainder. What goes in nicely typically has been a constant. Now it's a line, and that's going to be our end behavior. And then the function is going to be similar to what you see as the r of x. And we call these r of x and q of x. So the quotient part of it, and then the remainder part. And in summary, what we'd say is, for a typical rational function where f of x equals one polynomial divided by another, we can just do the divisor into the numerator, and everything that turns out nicely we'll call q of x. What's left we'll call r of x. That q of x ends up as the end behavior. The r of x helps describe the middle behavior. Here's our function then. We have a degree 2 on top, degree 1 on the bottom. We are not going to be able to find the end behavior easily, so we'll go ahead and do our synthetic division. We have a 0 on the bottom at 2, so when we plug that in, 2x squared 0x plus 4, we then do our synthetic division, bring down the 2. 2 times 2 is 4, adding, 2 times 4 is 8, adding gives us a 12. Our oblique asymptote is going to be 2x plus 4. All right, so here we go. Zeros, how do you make the numerator equal to 0? Well, in this case, the x being squared can't go negative, so adding a positive, that means we have no real zeros. The vertical asymptote is going to be at x equals 2. And the y-intercept, when you plug in 0, it just reduces down to -2, 4 over -2 there. We already know our oblique asymptote here. It's y equals 2x plus 4, and our math way of saying that is taking the limit as x approaches negative infinity on the left, positive infinity on the right. The function will approach negative infinity over there on the left, positive on the right. And that comes from thinking about a positive slope, how that would look. All right, let me clean this up a bit. Sign chart's going to have important value at x equals 2 for x. Beyond that, we go to the left. We know for 0 it's negative. We know on the right, very large positive over very large positive is going to give us a positive. Okay, and now we can draw our asymptote. We have a vertical asymptote at x equals 2, and then our oblique asymptote at 2x plus 4. 2x plus 4 means we are going to pass through x is 2, sorry, negative 2, and then go up a couple of times. I got to make sure I have space for my drawing here. So this y-intercept is going to be 4. If I go down 2 over 1, down 2 over 1, I'll end up over here. And now I think we're ready to place some dots here. So I'm going to go with a green marker. And we have a y-intercept at 0, negative 2. We don't have an x-intercept. And in order for this graph to be negative all the way, we have to approach this asymptote over here, pass through our y-intercept, and then approach the vertical asymptote. Likewise over here, if it's always positive, I've got to exist up in this area here. All right. Okay, let's try another one. I'm going to have you try this on your own. Let you know that you'll want to factor the numerator to get your zeros, and then also do your synthetic division. So hit pause and then come back when you're ready. All right, to get started on this graph, I'm going to get my synthetic division out of the way. Factoring should be pretty easy on this. I've got a 0 at negative 1. I've got coefficients of 1, 3, and negative 10. I bring down the 1. 1 times negative 1 is negative 1. Add 3, I get 2. Bring up the negative 2, I get negative 12. Okay, that makes it fairly obvious to me that I don't have a factor in the denominator that repeats in the numerator, so no removable discontinuity. I'll come over here and write then this is x plus 2 minus, or I'll put plus negative so that I remember that's like a flip, vertical flip. Okay, so that's going to be my transformed look. I'm also going to write it in factored form here. In factored form, these factors are x plus 5, factors of negative 10 that add up to positive 3 are plus 5 and minus 2. So we can tell our zeros fairly quickly there. All right, our zeros then are at negative 5 and at positive 2. And our vertical asymptote is going to be at x equals negative 1. The y-intercept, when you plug in 0, everything reduces. All the x values go away. I get negative 10 over 1. So I get 0, negative 10. And then the end behavior, well, we got that up here. It's f of x approaches x plus 2, or at x plus 2, that means negative when x is negative, positive when x is positive. All right, so our oblique asymptote here is y equals x plus 2. And now let's go ahead, I'm going to clean this up. Let's go ahead and make our sign chart and see if we can get a graph that looks like something here. We have a 0 at negative 5, positive 2, and at negative 1 there's a vertical asymptote. I think I'm going to erase some more stuff here. Okay. And with this then, I've got my vertical asymptote and my oblique asymptote. which is going to pass through 2, and it's a slope of 1, so it's going to pass through -2. So I'll go ahead and try to make it look like it hits there. And now I'm ready to do my graph. I'm going to use green. I know that -5, 0 lies on my graph, and +2, 0 does. It's got a y-intercept down at -10 somewhere. And I have a sign chart to make. I never made my sign chart. For my sign chart, when x is very negative, I get negative times negative, so positive over negative makes it negative. I can plug in a -2 here. I get positive, negative, so negative over negative. That means it's going to be positive. I already have my y-intercept here. I know that's a negative. And on the far right, when everything is super positive, everything becomes positive. And I actually don't even need to make this sign chart the way I did, just because I know my end behavior from my oblique asymptote and I defined it here. But it's good to check to make sure that you're accurate. All right, now let's sketch this graph. Connecting these dots, I'm going to have to go negative to the left, positive to the right, and approach these asymptotes. So something like this on the left side. And then over here, similarly, I've got to go through these dots. Something like this. All right.